Hello to everyone. Today I'm discussing about the structure determination from the Raman with the help of the nature of the light. That is whether we are using the polarized light or the unpolarized light. And as we know that if I'm using the plain polarized light, sometimes what happens that once we are taking that the scattering light in a perpendicular direction, you may have sometimes a plain polarized light or a linearly polarized light. And then depending on theoretically, we'll be looking that when you have input light is a unpolarized light, depolarized light. In the output, once you have a polarized light, linearly polarized light, we'll see that what sort of this structure is. So then theoretically we'll define that what is the parameter to say that it is a depolarized up to this level, and it is the when it is a symmetric and it is a asymmetric mode. And to check it, and we will be taking that the tetrahedral structure of the methane, that is CH4. So we know that if I have any light, if it is a any orientation or it is a linearly polarizer, suppose I am putting a polarizer over here, then I am taking a certain sample over here, this is my sample, then scattered light if I am measuring with an analyzer. So if it is linearly polarized light, suppose the intensity is I, and if analyzer is with respect to this is, again I am putting the angle of this one is parallel to this one, then this depolarization rho is defined that is rho perpendicular to this rho of, sorry, this I perpendicular to I of parallel. It means that if I have a linearly polarized light, after the sample is scattered light having some perpendicular one. If you look at for the linearly polarized light is for, you have linearly polarized light, suppose vertically polarized light, and if you are putting that analyzer after the sample analyzer in a vertical angle, then you have a maximum intensity, I max. If it is a horizontal direction, that is a perpendicular to that, is intensity must be the minimum. Now what's happening here, what I'm saying that if I have a linearly polarized light and even an unpolarized light, if then the depolarization is defined as rho is equal to I perpendicular to this rho 1. If rho I is equal to 0 at the same one, that's what we are saying is simple in a Miller's law, then rho is equal to 0, this I perpendicular to 0, this rho is equal to 0, it is a completely polarized. On the other hand, if rho perpendicular I perpendicular divided by I parallel is equal to 1, it means that it's completely depolarized. And if the value of rho is in between this 0 and 1, that is called the partially depolarized. So the degree of the depolarization. So with the help of the degree of the depolarization, we are estimating the structure of the molecule. Now keep in mind that how this depolarization parameter we are defining, we'll see that how it happens in our, it is helpful to find out the structure of the molecule. So the simplest example I'm taking that the vibration of the spherical top molecule, vibration of the spherical top molecule, vibrations of spherical top molecule, that is CS4 as a good example of the spherical top molecule. So you have this C, H, 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 and this H. This H, and so you have now during the vibration, the CS bond symmetrically extending, stretching, or contracting. So what will happen that once we will look at this is polarized sphere, so the polarizity will be the spherically symmetric one. So I will be getting that the spherical symmetry of it. Then you have a C, H, 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 and this H. So what will happen that either the size of the bond is very, this in a phase it increasing or the decreasing. It means that the shape of this spherical symmetry of this polarizability ellipse remaining the same. So sometimes what we are calling that the reason that the motion is often referred as the breathing frequency. That is the breathing frequency. It is the increasing, decreasing symmetrically. That is called the spherically or the breathing frequency. It's the plainly Raman active because it is changing, polarity changing, but symmetrically it is changing. So that is called the plainly Raman active. Now, so we are considering two cases. Now what happens that for this structure, beam of unpolarized radiation falling on its molecule. Suppose I am considering that an unpolarized light is falling on a molecule. The propagation of the axis of this radiation is g direction. Since all the diameter of the sphere are equal and the molecule is equally polarizable in all the direction, the induced dipole is the molecule will be along the direction of the greatest electric field, that is the exciting radiation, that is the perpendicular to the field. So this is my molecule. So the radiation is falling on it. So toward this one. So means that this is the sphere, then I'm falling in this direction. So I have this is x, this is y. The radiation is falling on this fashion. So you have this x, this is g direction, this is y direction. So you have the radiation in this fashion is falling on it. As I said that now the radiation is falling in this sphere in this fashion, then I am measuring somewhere from here. I am taking this scattered light. The diameter of this sphere is all in all the direction because it's a spherical symmetry. The induced dipole moment the molecule will be along the direction of the greatest electric vector in the exciting radiation, that is the perpendicular to the direction of the propagation. Thus the induced dipole moment will lie in my xy plane. Now the induced, because this is my beam, this is my xy plane. So the dipole moment will be induced dipole moment will be the xy plane. So and where the incident beam with the electric field vector a vertical xzy plane. So now the another one, again the same way, this is x, this is y. Now I have this field in certain different direction. This is making an alpha now. This is my x, this is my z. Then I have this radiation. It is making some angle of alpha. Initially I have this polarization in a y of z plane. Now this from the yz plane it is making some angle now, this alpha angle. So in both the cases induced dipole will be in the xy plane. And the incident radiation having all the acceptable angle of this alpha. So to an observer studying the scattered radiation at a right angle to the incident beam. So with respect to this incident beam, we are observing that radiation, that output or the scattered light at a perpendicular to this one along the x-axis. The oscillating dipole emitting the radiation is conformed to the xy plane. The radiation is plane polarized. So the radiation is falling in this one. I am taking the perpendicular to this one. The induced dipole moment will be the where this my incident is intense one, that is the in xy plane. Then the radiation is taking particularly, if I have the radiation in this plane and this oscillating in this plane, then I have this oscillating field is completely the output field I am getting the linearly polarized or the plane polarized. Whatsoever this angle of this alpha, because I am taking the perpendicular to this one. So when the molecule undergoes a breathing vibration, that the polarity ellipsoid remains spherical and the dipole changes remain in the xy plane. So whatever the breathing frequency of this one means, that is symmetrically extending, bond extending, or the stretching or the contracting, then all time I have this dipole moment in xy plane. For the vibration lie with the completely plane polarized, that's rho is equal to 0. It means that the depolarization is equal to 0. Depolarization is equal to 0. Means there is no depolarization at all. Because we have an unpolarized light from here, then you have getting the output at the. So in this case you have you are putting that is perpendicular to this one, then is depolarization equal to if depolarization rho is equal to 0, quite irrespective of the nature of the exciting radiation. So now once you have this phenomena, then the breathing frequency, with the breathing frequency, the dipole moment is changing, then output you are getting the completely polarized light, linearly polarized light. So this is the case of the symmetrical case. Once you have a breathing frequency in a phase, this molecule is, the polarity of this symmetrical, spherically symmetric molecule is changing in a phase. Now if I consider another example, if I have a very little bit of the asymmetry of the molecule, this is my H, this is C, and this is H, and this is H, and this is H. So these are moving in this fashion, and this is also moving in this fashion. Means they are not contracting symmetrically or not expanding symmetrically. So what will happen in this case? Then C of this H, 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 and this H. So polarity ellipse is no longer the spherical one, little bit of the spherical one now. So when CS bond stretches while the other three contracted and vice versa, during the vibration of the polarity surface, loses its spherical symmetry and becomes ellipsoid at the extreme of the vibrations. On such extreme, we have defined by this spherical surface. Now the one exciting radiation interacts with the molecule, induced dipole moment will be greatest along the direction of the easiest polarizability. So the easiest polarizability of this one is along the my minor axis. It was a symmetrical one, all the direction it having the same one. But in this case, due to this little bit of the asymmetry, so the maximum polarizability will be the easiest axis of this polarizability ellipse. So the easiest polarity dimension are the minor axis of this molecule. So in a sample molecule, these axes will be oriented in the random direction. You have this is the three-dimensional surface. You have a random direction. Any direction it can be of the direction to the incidence. So because the lack of the spherical symmetry in the vibration, the induced dipole moment will be randomly oriented, and the observed Raman spectra will be the dipolarized now. Because it all the direction. There it was a fixed now in an XY plane only. If it is a XY plane only, then you have this vibration only along the XY plane only. Now in this case you have all the, because the spherical symmetry, because you have this ellipsoid in this fashion, that you have all the direction you have in the shape. So the orientation of this dipole, the induced dipole moment may be any direction of it, but along the axis of this my minor axis. This is this minor axis side. So then the output will be depolarized. Means the output will be depolarized. It means you are getting the sum of the intensity at the perpendicular direction or the other orientation of your analyzer. So now, with the help of such kind of the mechanism in the Raman lines, their appropriate molecular vibration in the case of the methane, the totally symmetric vibration gives rise to a completely polarized Raman line, whereas the non-symmetric vibration gives the depolarized line. So the degree of polarization of the spectral line can be easily estimated by noting by the intensity of the each line varies with the piece of the Polaroid or any analyzer. So what we could do, at the output we can put our polarizer or analyzer, we can rotate it and we can find out the polarization of your emitted spectrum or the spectral lines. and we have kept that this z is my this direction of my incident light. So with the help of this one, this depolarization and the polarization, we can find out the symmetry of the molecule and the asymmetry of the molecule. So now extension of the some other type of the molecule of the same phenomena. So now, as we have just precisely calculating that the somewhat this argument that once you have a linearly polar slide, we are saying that it is a symmetrical molecule, and if little bit of the asymmetry there, then you have some depolarization over there. So theoretically, if the degree of polarization rho is less than 2, this one, if rho is less than, theoretically it is defined as rho is less than or equal to 6 by 7, that is 0.855. If the depolarization is less than to this one, then the vibration concern is symmetric. So the vibration are concerned to the symmetric, and if rho is greater than the 6 by 7, then line is depolarized and the vibration non-symmetric. So if you can loosely speak that the molecule with the increasing symmetry, that is the linear molecule, are less symmetric, then the symmetric top molecules turn to be less symmetric than the spherical top, and then the higher of the molecular symmetry of the smaller will be the degree of the depolarization of the Raman line for a particular type of the vibrations. So now the least symmetric will be my linear molecules, linear diatomic molecule. Then bit symmetric will be top symmetric molecules. Then the symmetric molecules will be spherically symmetric molecules. So we can see that the usefulness of this depolarization measurement by considering the simple example, the molecule. Now another example, this N2O. The observed spectra for the Raman for this N2O, this new centimeter inverse 589 at 1285 and 224 centimeter inverse. So infrared strong PQR contours you are getting, and this at corresponding to this one we are getting that the very strong PR contours, and the Raman, there is no Raman over here. Here, very strong polarized and strong depolarized. So once we are studying that this N2O molecule corresponding to this wave number, we are getting the very PQR contours, that is PQR bands, but there is no Raman at all. For this wave number, we have very strong P of R contours, very strong polarized, and 22, 24 very strong PR bands, but strong depolarization. The strongest line these spectra collected in this table, and their band contours the infrared and the state of the polarization in the Raman. So this data tells immediately that the molecule has no center of symmetry. The Raman and the infrared line occurs at the same wave number because it has no center of the symmetry. Because if center of the symmetry, then it must have some line. But here you have a strong one, you do not have it. That is a principle of the exclusion principle. So the structure is not, it means that it is confirming that its structure is not NO of N, not a center of symmetric molecule. Rather, the fact that the infrared band have a PR contours indicates that the molecule is a linear. Because you have a PR band, it means that it is a linear one. because for the linear only you are getting that strong PR bands. So this first molecule definitely have the linear but not a center of symmetric, then it must be the NN or O structure. And the molecule have the mode of the vibration is defined as 3n minus of 5. Is equal to 3 atoms are there, then minus equal to 4. But you have only the 3. You have the 3 bands only. 3 bands only corresponding to 3 vibrational modes. It means that you must have the one mode, stretching mode would be your degenerate one. So the symmetric one, so corresponding to that you are getting the same energy. So fundamental mode, what two of these, or the bending mode, sorry, not a stretching mode, bending mode will be the degenerate. All 3 different fundamental frequencies should be both infrared and the Raman active. But you know that the perpendicular infrared plainly to be associated with the bending mode does not appear in the Raman. It is not appearing in the Raman. This accords with the expectation bending modes are often weak and even unobservable in the Raman. So the bending modes are unobservable and very, very weak in a Raman spectroscopy. So we are left with the assignment to this corresponding to these lines, these bands 1285 centimeter inverse and 22 or 24 centimeter inverse, that bands of the symmetric and asymmetric stretching modes. Both infrared have the same PR parallel contours, but we know that only 1285 centimeter inverse is a Raman polarized. This is a Raman polarized line. And then assigned the symmetric mode, leaving that this band is the asymmetric one. This 22-24 bands is the asymmetric one because you have a depolarized one. So it means that in this you have a symmetric modes for the stretching one. In this case you have a very depolarization. So it polarized, it means that you have a symmetric mode, you have a asymmetric modes. So the overtone and the combination bands would also be studied to ensure that their activities and the contours are the arguments with the molecular model proposed. The fine structure of the infrared band also support the structure, and finally isotope substitution leads to the change in the vibrational frequency to excellent agreement with the model of the assignments. So in this rather a simple case of polarization data were hardly essential to analyze, but certainly it is a useful, but it's not essential, but these are the very essential, certainly useful. So we can take a more complicated and valuable once we will be considering that the IR spectroscopy as well as the Raman spectroscopy, then it is always easier to find out the structure of the molecules. So as I said that and repeatedly I said, in conjunction with my Raman spectroscopy and the IR spectroscopy provides a proper or the essential tool to determine the structure of the molecules. So here in the how this polarization is important, it is a useful, but certainly it is not essential to find out your structure of the molecule. So then I thought I will be concluding here today itself for the Raman spectroscopy, but I am unable to conclude this part. Again, I need to discuss about the structure determination from the Raman and infrared spectroscopy. So we'll see that. I will discuss it now later.